Hey everyone, we're on to the next lesson here, still talking about acids. This one is dealing with acid strength, strong versus weak acids. So when we're talking about acids, what exactly do we mean when an acid is a strong acid? And what do we mean when an acid is a weak acid? So some examples of strong acids, and I'll show you a little bit later where you can actually find this. So acids like hydrochloric acid that I've been using in examples before, that is a strong acid. Nitric acid, sulfuric acids, these are some of the strong acids and some of the common ones that we do talk about as well. So when we use the term strong, it's not the same as saying something is concentrated. So when we talk about concentrated, we're talking about the units of moles per liter. So we can have something that is very, very concentrated. For example, 1.0 moles per liter is a fairly concentrated solution when we're talking about an acid, whereas if you have something as 0.01 moles per liter, that would not be a concentrated solution. But the term strong is completely different than the word concentrated. So we can have an acid that has this concentration, but it's weak. We can have an acid that has this concentration, but it's strong. So again, they have different meanings, and we'll see exactly what that meaning is in the next slide here. So if we take a look at two fairly common acids, so acetic acid and hydrochloric acid. So interestingly, as I have here, both of them may actually be present in your stomach. So acetic acid that you put on your food, your French fries, it is really just vinegar. Acetic acid is vinegar, and it is one of those carboxylic acids that has the ending COOH, where it's this hydrogen here is the one that is donated to the water. And also in your stomach, cells lining your stomach, some of the cells do actually produce an acid that helps to solubilize the food, and that is that hydrochloric acid that we've come across before. So these two acids, as we will see, they can have exactly the same concentration, but in terms of strength, they are most definitely not going to be the same. So these are those two acids. So I do have right here that our carboxylic acid, again, this is the indication that it is going to be an acid, the COOH. This is the one here that's going to be donated, that proton being donated to the water, and that's what makes the water in this case being the base, and the acetic acid being the acid. So what we get on the other side is our acetate ion, and again you would find this on the table of polyatomic ions, and of course our H3O+. And as this goes up, the pH is going to go down, so that is going to drop the pH away from a neutral pH, and that's what makes this an acidic solution. So as it turns out here, the pH ends up being somewhere around a pH of 3. So if we do take hydrochloric acid, this is now a strong acid, exactly the same thing. It's this proton here that's going to be donated over to the water. What we're going to get on the other side is the ion, the chloride ion, and again we're going to get some of the hydronium ion that's being formed, which once again, just like above, is going to end up dropping our pH, making it an acidic solution. This one here, however, the pH is going to be much lower. It's going to have a pH of 1. So again, keep in mind that we only have a difference of 2 pH values, but it is a logarithmic scale, so that's actually a 100 times difference in terms of the concentration eventually and in the acidity of each of these different acids. So what exactly is going on with these two different acids that we have here? Let's talk about the strong acid first of all. And this was mentioned on a previous presentation that the protons associated with the hydrochloric acid, it is all of them that are donated. On the product side, there is no hydrochloric acid in any way whatsoever. So what we say is that 100% of those protons are donated, or we have a 100% dissociation. This is completely torn apart and all of the protons are donated. So this is how we can say as well that the concentration of the hydrochloric acid, whatever the concentration of that hydrochloric acid is, that's also going to be the concentration of the hydronium ions that are formed on the product side. Okay, that is the case with strong acids. Now let's jump up to our weak acid that we have here. So in this case, yes, we do have protons that are being donated to the water, but we also have on the other side, some of these protons are going to go in the reverse direction and they're going to be donated back. So we don't have 100% of the protons that are donated. In fact, it's only about 1% of the protons that are donated, and it ends up being a much larger number, like 99%, that are going in the opposite direction when this reaction is at equilibrium. And remember that the pH is determined by the hydronium ion concentration. So if this is 1% and this is 100%, well, that's 100 times difference in terms of the acidity, and that's why we see these differences in the pH. So let's take a look at some calculations and how that works out. So this is your definition of a strong acid. Strong acids, they dissociate 100%. 100% of the molecules dissociate. You should remember that. That is our definition of a strong acid. And it's only for these ones that we can take the concentration of that acid and say that it is exactly the same as the concentration of the hydronium ions. And that's why we can plug that number directly into this equation. And that is why for the hydrochloric acid, when you plug in the negative log of 0.1 moles per liter, that's where we get the pH of 1. So an extremely acidic solution that we do have here. For the acetic acid, you wouldn't have to do a calculation like this for Science 30, but I did mention already that it's only about 1%, so 1/100th of that. So now this is exactly the same concentration as the hydrochloric acid. So we have two acids that have the same concentration, hydrochloric acid and acetic acid. But one is a strong acid, one is a weak acid. So when we take a look at the hydronium ion concentration, it's only 1% of the acid concentration, which is this. This is 1/100th of that. So now when we take this number and plug it into this equation, well, we get a pH of 3. So again, 100 times less acidic than the hydrochloric acid. They started off with the same concentration. What is the difference? One is strong, one is weak. One dissociates 100%, and that's a strong acid. Any weak acid it dissociates anything less than 100%. So you can have a weak acid that dissociates 80%. It's still a weak acid because it's not 100%. You could have one that dissociates 70%. It's still a weak acid because it doesn't dissociate 100%. In order to make it a strong acid, it has to dissociate 100% of the protons do need to be donated. So in Science 30, we don't really talk as much about bases, but we could do something similar to determine if a base is strong or weak. So in the case of a weak base, we would not get as many of the hydroxide ions formed. And for a strong base, we get more of them that are formed. Okay, so fewer in the case here, the maximum amount formed if we do have a strong base. So that means that, well, both of these would increase the pH. But if it is a strong base, it would increase the pH much more. Many more hydroxide ions that would be forming. This is a table directly from your data booklet that you should become very, very familiar with. So this is the relative strengths. It's comparing various different acids. It doesn't give us actual numbers in terms of percent dissociation. It's simply comparing one acid and base to another. And all of these are at this concentration, and this is the temperature that they're at. So we have a list of a whole bunch of acids going down the left-hand side. And what's kind of nice here as well is it gives you the acid formula. So even if you're not great, you don't remember the rules for naming acids, chances are for Science 30, any acid that you are given, you're going to find it somewhere on this table for the relative strengths of acids and bases. And what we also have here is the conjugate base. So I'm going to go back a couple of slides here. I mentioned it on a previous presentation, but let's go back and talk about it here as well. So when we talk about these weak acids, we do have our base, which is accepting the proton, our acid, which is donating the proton, but because this can also go back in the opposite direction, what that also means is we also have an acid and base on our product side. So on our product side then, what is now donating the proton is going to be the hydronium. So this is going to be an acid because it's donating protons, but because it's on the product side, we call it the conjugate acid. And the one that's accepting would be the conjugate base. Okay, and yes, for Science 30, you do need to be familiar with those terms as well. So back to the table of acids, acid formulas, and the conjugate bases that go along with it. So the nice thing about this table is it does tell you with this arrow, increasing strength of acids. What does that mean? Strong at the top, and as you go down, they get weaker and weaker. Okay, weakest at the bottom. So this is just a sampling of acids. This isn't all of the acids, but this is all that you will need for Science 30. So this bar right here, the shaded bar, it's really important. Strong acids are these ones here. Okay, so whenever you see these, they are a strong acid. Anything else, it is a weak acid. And we can rank them because it's increasing strength. So in terms, again, of the acids, if we were to take a look at this one, this one, this one, and this one, this is the strongest, followed by this one, and the acetic acid. Okay, all you need to do is go down the table, and that's from strongest to weakest. We have the formulas, and now on the other side, we have the conjugate bases. And it also tells us here, increasing strength of the base. So these ones here would be the weakest in terms of the bases, and at the bottom, they would be the strongest in terms of the bases. So now we could take a look at a question like this. So these four different acids, nitrous, sulfurous, ethanoic, and sulfuric. So be kind of careful. This is sulfurous, and this is sulfuric. So if we go back to the table, take a look at where those are. Okay, here's sulfuric. It's going to be the strongest, so that's going to be our number one. Here is sulfurous acid. Maybe I'll just circle these. We had sulfuric. We had sulfurous. We had nitrous and ethanoic. Again, there's a nitric, but it's not this one here. It's the nitrous. This one here, and the ethanoic, it is the acetic acid. Okay, so in terms of the ranking, sulfuric, sulfurous, nitrous, acetic. Strongest, sulfuric. Oh, sorry, this is from the weakest to the strongest, so make sure you always take a look at that. Make sure you're reading it carefully. Don't make any assumptions. So here we are taking a look at the weakest, first of all. So that would have been the ethanoic, followed by the, which one was it? Nitrous, sulfurous, and sulfuric. Conjugate bases, we won't go through this one, but it's the same thing. We're just using the conjugate bases on the right-hand side, taking a look at these and ranking them once again. And in this case, it's from the weakest to the strongest.